Let me start to record. All right. Hello, everyone. Is everybody able to hear me clearly? Hi, Ankit. Hi, Balvinder. Hello, Josephine. Hi, Pavan. Hello, Ravichandran. Hi, Ravindra. Hi, Robert. Hello, Tracy. Great. Great to have you in session. And okay. All right. So, is there any question before we start? All right. All right. Should I proceed, or do you have questions for me before I start? There'll be more people joining soon. Okay, great, great. So, how many of you were able to run the streaming job? Did anybody try the streaming job? Did you try to run it? Okay, great, great. Now, all right, all right. Okay, okay. Which part do you want me to explain, Josephine? Do you want me to explain the map reduce, or do you want to explain the streaming streaming job, or do you want to repeat this one? Okay, so Josephine's question is, what if there is no input folder? Good question. So generally, the way you run Hadoop jobs, you should have the input folder, and on that basis, it's decided what to read from data. Okay? If you do not have an input folder, you just point the input to an empty folder. That should be okay. All right. Create an empty folder and you point it to. All right. And it's okay to share the question with others so that I don't have to repeat the question for everyone. Okay. Yes. All right. All right. So, okay. So what is it? So let me explain again. So we talked about from the beginning. We talked about why do we need big data and what are the various use cases. Then we went into HDFS. We understood how we solve the problem of volume. Then we went into we tried to understand how yarn works, meaning the how do the programs get distributed across the cluster. Now, what goes inside a program is something with which we are discussing right now. So MapReduce is one such a structure of programming a distributed work. Okay, so we discussed about how does MapReduce work. Okay, we discussed about how does MapReduce work, and then we talked about practical way of executing MapReduce by using streaming and by shipping the script and others. All right. Okay. Okay. So let me go back to the diagram once quickly, and then so that we all are on the same page. Okay. All right. All right. So actually, I'm connected to the wired. Earlier, we were facing last week we were facing problems related to the connections. So I had got the wired connection now, and the wire is directly going into my Mac. So that means the connectivity should be good now. Okay. So let me just go over this diagram once. All right. So that everybody. So this is the typical flow in MapReduce. Okay. So as we know that in HDFS data is already spread across on multiple machine in the form of data blocks, HDFS block you can also say them. And on top of every HDFS block, input splits are created. Input split is a logical form of raw data block. We will go into this translation of the data block and the input split. Input splits are made up of records, and in our case, the in record is what is the record? Is a single line because we are processing text. So a split represents bunch of lines. Okay, it's a set of lines or a data set of lines. On every line, your map function is executed. The the output of map is collected and ordered. And after ordering, the keys. So since map will be spitting out key values are put into these buckets. Some of the keys go into the bucket, some of the keys go into another bucket. Okay? So essentially this mechanism divides the workload to multiple reducers, and these buckets are taken to first bucket goes to the first reducer, second bucket goes to second reducer, and so on. And after taken, since both the buckets are internally sorted, it's easy to merge all the buckets coming from all the maps. Okay, a quick question to all of you. Had there been, so right now, there are three maps. Why there are three maps? Because we had three data blocks. Okay, our file must have been how much? Guess? Anybody? Size of our, since right now there are three. Okay, all right. So you can see, just give me a second, and what's the date today? 19 June. 19 June. Okay, so here my question to everyone is, We have, say, 3 blocks here, right? How much would be the size of file? Anybody? Greater than? Greater than what? And lesser than what? Yes? Great. Thank you, Balvinder. Thank you very much. You have answered in the format which we wanted. Great. All right. Great. Thank you, Pawan and Kumar and Josephine. All right. So we have 3 blocks. So there would be, so our file should have been greater than 120 MB, which means greater than 2 blocks and lesser than 4 blocks. Okay. All right. Good. Good. Great. Now, so it's clear to everyone. Next is that there are how many reducers are there? 2 reducers. So we decided on number of reducers. So total transfer you can see is from every mapper, data would go to every reducer. That means how many transfers are there? 1, 2, 3, 4, 5, 6. Okay. The question to all is, if we had a file of say 1 GB and we specify 4 reducers, how many total data transfers would be there? Yes? If you were processing 1 GB file, okay, and that's an input file, 1 GB input file size, and we specify that we need 4 reducers, then how many total data transfers would be there? Yes? Anybody? So 8 will be blocks, right? Total number of blocks will be, so total number of unique blocks will be 8, right? And number of reducers is how much? 4. So total, so 8 mappers transferring to 4 reducers. That'll be how much? Because every mapper node will transfer the data to every reducer node. That means it'll be 8 into 4, correct? It'll be 8 into 4, and that'll be. So the question here we are trying to answer is this. If we have 1 GB file size which we are processing and we specify that we need 4 reducers, how many total data transfers would be there? So there'll be total 32 network connections. Every mapper trying to transfer data to every reducer. Good? Great. All right. So once data get merged on every group, the reducer is called. The output is saved in the HDFS. All right. So I hope everybody is clear. So Josephine, this is what you wanted me to repeat. Yeah. Okay. Great. Now let's move on. Now, so we were able to break down our problem into maps and reduces and use this script. All right. A very brilliant question from Balvinder. If our shell script had some dependent file, or if we had to pass multiple file, then does minus file, yes, supports it? Yes. Let us say, let us take a case here. Okay. Let's say this was another script. So we were having some more script here. Let's say myscd.sh. We have written some custom scd and we want to, this is our mapper which calls scd, passes to myscd.sh and then does something. The question is, what do you, how do you send these files? So you add one more minus file here saying myscd.sh. All right. Make sure that myscd.sh is uh, executable, meaning it should have first line stating the correct way to run it. Or maybe we have written this in Python, so we will basically pass this along. Okay. So in this way. All right. I hope that makes sense to you. Okay. All right. So basically, this is the right way of handing over the work to Hadoop streaming. Okay. So whatever are your dependencies that are not deployed need to be either you install my cmd.sh on every machine. The other way could have been that we copy my cmd.sh into a place which is in the path of every machine, meaning it should be in some user bin or slash bin, somewhere like that. Okay. Then the normally it would be treated as if it's an inbuilt program, and therefore we don't have to copy it, right? So this is what lots of people do. Lots of people, what they do is when they know that a particular program is needed again and again by various libraries, they copy or install it using the other tools such as Puppet. Okay. Using Puppet, we could install anything on multitude of machines. Why we need Puppet, by the way? Because generally a cluster contains hundreds of nodes, or even if it contains say 20 nodes, it's actually very Herculean task to get something done. Okay. In case of CloudX Lab, we had to write couple of similar tools so that we could manage the whole cluster quickly, because we have to execute same command again and again on every machine, which is quite a hectic work. All right. Okay. So all right, next is good. A question from Ravichandran is, Yarn will not do the task. Yarn will do the task. Yarn is good for general workloads, but most of the sysadmin kind of work are better done through Puppet-like utilities. We can tell Puppet that keep running a particular program. If that exit, it keeps on running and running again and again. Using Puppet, we can do installations. Okay, while Yarn can handle the workloads, but not this kind of workloads. Or you can say that it's far more easier to do installations using Puppet than Yarn. All right, great. Okay. Question is from Samip. Where does this file located? This is in HDFS and the output is also saved in HDFS. Okay. Is that question? Yeah. Yeah. That's right. So this is on HDFS. Because only then it'll be able to figure out what are the blocks, it'll be able to figure out what are the blocks, where are they located, and accordingly number of map tasks are decided. If it is located in local file system, then there is no HDFS and no distribution of work. Therefore, Hadoop, because every component that will study further, most of it would basically run on the data stored in HDFS. They all assume all of the tools that we will study further, they all assume that the data is in HDFS. And all of the data that the only reason why we are using MapReduce, because we don't, it's not fun to use MapReduce. It's not a design pattern to use MapReduce. We are using MapReduce because we will be processing humongous data. Okay, and it's better to keep humongous data in HDFS than the file system. All right. Akash's question is, do find command work in HDFS? Sadly, it doesn't. Okay. All right. So Samip's question is, any file located in Hue, meaning HDFS, can be used as the input for a streaming job. Yes. Okay. Great. The other important part is, while this is expected to be in HDFS, this is supposed to be in the local file system. Okay. Similarly, when we are shipping something like this, mycmd.sh need to be in the local file system. The program is in local file system, data is in HDFS. All right. All right. So we have gone through the hands-on demo. Now here are a few notes. We will talk about these again maybe, but yeah. So one more thing is that it's okay to have no reducer. It's completely okay to have no reducer. You can try to run, you can test it out, your streaming job without the reducer. Okay. In that case, if you are trying to use a program without a reducer, the data would directly go to HDFS, meaning data from here would directly go in HDFS. Okay, so this place. Can I draw like this? Data from here, from every machine, would directly be saved in HDFS. All right, you can try to run these programs, the previous programs, without a clause of reducer. All right, you can try that out. You remove this line and try to execute it. Okay, next is, and in case you do not want sorting, it's generally advisable that after removing reducer, you also mark that we don't want any reduced tasks. So it will not do the sorting. And in such case, when there are no reducer, Mappers will decide the number of output files. If there are 50 map tasks are being executed, there'll be 50 parts in HDFS folder, in the output folder. All right. Now question is, how many number of maps are there? Number of maps, as in number of map tasks or number of mappers, is a function of input split. It's a function of how many input split do you have. Okay. And sometimes, as someone was saying, that what if we don't have an input data to what if we want a distributed work, but we are not operating on HDFS file? That's also completely okay. Okay, let's say our data is not in HDFS. And who is such an example? Let me give you an example. Let us say we have our database in MySQL and we want to pull the data from all the nodes and then save it in HDFS parallelly. Okay, so if we have hundreds of nodes in Hadoop cluster, and we have this powerful MySQL machine in which our data is stored, and we want to read parallelly from this MySQL. So we generally use Scoop, which is part of Hadoop ecosystem. And what does Scoop do is Scoop internally creates a mapper task. It doesn't have a reducer. It creates a map reduce task which doesn't have a reducer. And in the mapper, it essentially connects to MySQL and then gets the data from everywhere. So in the case which I've just mentioned where we are reading data from MySQL, we don't need the input data. We basically point to an empty folder, or I think it's okay to skip even the input folder, but I'm not sure. Generally it forces me to put the input folder. So so in that case what would happen is the number of maps will be decided by the logic that you put in. So So number of maps in the cases where the input data is not in HDFS, and in those cases we may want to enforce the number of maps from our side. Okay, in those cases we may want to, right? So if you are configuring this from Java code, you can say conf.set num map task. In case you are using a streaming job, you can say -d maprad.map.task equals 1. Okay, that's how it is. So if you want, say, 100 map tasks, you can say 100. If you want 2 map tasks, you can do 1. So you can control number of map tasks, although by default it is decided number of map tasks are a function of the input data, but you can control it by yourself as well. Okay, and the use case as I've given you, that let's say you want to pull in the data from MySQL parallelly on many nodes. Okay, so because map task could contain anything, it could contain the logic to send emails, it could contain the logic to connect to MySQL, or anything it can do. Okay, so if your code is connecting to say MySQL parallelly without depending on number of blocks, in those cases you can set explicitly the number of map tasks and control number of mappers. All right, now this is uh, little you know looks little strange, that a lot of times, a lot of people ask, how do you decide number of reduced tasks? We said two earlier, we got two output files, but how do you generally decide on number of reduced tasks? Okay, So in very simple words, it is done generally in a what do you call hit and trial method. Okay, you try one, then increase, decrease, and so on. Okay, that's the straightforward answer. A little more sophisticated answer is that first find out how many how many maximum tasks can be executed on your cluster. Okay, so when we configure yarn when we configure yarn, at that point of time we can specify how many tasks each machine is supposed to execute. All right, and how do you configure that? Why do you configure that? Because some machines might have 4 cores, 2 cores, and some machine might contain 8 cores. So you generally want to have one task per core. Okay, by default, every machine eh, can execute 2 tasks in parallel. All right, so the maximum number of reduced tasks that you can execute in parallel on a machine is configured, and by default it's 2. Okay, the total number of tasks that a whole cluster can execute in parallel is summation of all the nodes. If all the nodes can execute equal number of reduced tasks, then you can just take number of nodes into max reduced task simultaneously per task tracker. Okay. Now, as you can see that whatever tasks are there maximum possible, either a fraction of it, 0.95, 95% of the total task should be your reduces, or 1.75 times the max tasks. Okay, so your number of reduces should be between the two. All right. Now, keep in mind, if we are talking about very small data and very small computation, that you know that it can be done by one node very comfortably, then you don't need to go for this calculation. Okay. Generally, if you keep on increasing number of reduced tasks, okay, even though the work might get sometimes faster, but there are more chances that you will increase the framework load, and hence you might increase the framework load, and hence the system might get slower often. Let's say we are right now handling 6 MB. Okay, the work is pretty small. There are hardly 10,000 unique words. Okay, there are hardly 10,000 unique words in that file. Now, if you try to distribute these 10,000 tasks, 10,000 words on say 10 machines, it's an unnecessary kill. It's unnecessary because we are not doing much in the reduced task. We are just counting it. Okay. So even though increasing reducer means that the work will get done faster, but it will also increase the framework load. It will also increase the framework load. And if you have more reducers, you will have lesser chance of failures. Why? Because the work, let us say a particular reducer failed, the work will quickly be handed over to another machine. Okay, so only a small chunk had failed and we have taken the corrective action, rather than if there were only 2 reducers and one of the reducers failed. Now that half of the work will have to be kind of redone. Therefore it lowers the chance of overall failures, increasing the reducers. All right, now let's get back to these problems which we had left in midway. Do you want to take more examples before we jump into this? Okay. All right. All right. Samip's question is, can we get one more example of on streaming? Yes, we can do that. So, all right. Let me see if I have something ready. Otherwise, okay, writing from scratch might waste. Uh, uh, I'm actually in Ajay Reddy's account. So if you log in into No Big Data, the chances are that you will be logged in into CloudX Lab automatically. Okay. Ouch. And okay, I have to open this one, not that one. All right. So here we are. This is the console. All right. So this is the console. And here, let me just see if I have some Python program. Okay. So we have one Python program called replace. Okay. And do I have new replace? Let me just see if I can. All right. All right. So you can see that this is one of the programs which I have written earlier. Let me just copy this. Okay. And I say, we call it movie lens ML map. Okay. ML map.py. All right. So be with me as I walk through this. Okay. So what is it that we are going to achieve right now? We are going to solve the problem of year-wise ratings of movie in the movie lens data, right? Okay. So here is you can see the data, not this one. There is a folder inside a folder. Okay, so here is our movie lens data, and we are calling it ratings.dat. Okay, so we are going to use ratings.dat. We will split this record using Python. Okay, is anybody familiar with Python? Okay, okay, only Samip is comfortable with Python. Never mind. So I think it will be easier for you. Ajay and Samip only are comfortable. Who else is comfortable with Python? Josephine is good, good. All right. Now, what I'm trying to do is I have opened an editor. Okay, it's called Vim editor. It's a VI editor, or I can actually open another editor called Nano. Okay, or let me just put it here. Okay, this is good. In Python, it's important to have the indentation. Okay, so I'm going to have the indentation properly. Okay, so this was the another example. Let me say, so okay, let us say my each line is made up of the movie lens data. Okay, all right, never mind. So this is the file that we want to process. Okay, this is the file which we want to process, and what is it that are trying to achieve? We which one should we do? Is it okay? We want to compute for every movie how many people have rated it. How many people have rated a movie? Okay, so let me just write it down. How many people have rated a movie? Okay, so how do we find out? Anybody? So what should be our map? This is our input file. It has got first column as user ID, second column as movie ID, third column is the rating given by this user to this movie. So one has given 5 to 21193. Okay. Now what do we want to do? We want to find out this movie is rated by how many people? This movie is rated by how many people? Okay. So, all right. So, okay. Pawan says that mapper should give out movie ID and one, and reducer should just say movie ID and sum and count. Good. Now, do you think it can be done using the console, using the shell? Yeah. Good. Good. I believe that it can be done, but let me say that the mapper side. Let's write the code for it. Okay. So what is the first we split this record because our map function is going to get executed against every line from ratings.dat, right? So we need to break this down into these four fields, and then we are going to print only the movie ID. Good? We're going to print only the movie ID. So let me open this is my Python console. From here, if I say things like split and good, it has splitted the data into these. Okay, so I could say comfortably user ID, movie ID, comma, ratings, comma, time, stamp equals this. Now you can see that if I check what's inside movie ID, it's 1193, user ID 1, ratings 5, timestamp this. All of these are strings as of now. Okay, so what are we going to do? We are going to say here for every line, okay, for every line in the input, okay, we are going to break down, we are going to break down this line into these fields, correct? I'm going to break down, say, this full line into this, correct? So let me just go back and try this. All right. So for every line that is given in the input to my mapper program, this is what I'm going to do. Okay. So this is a way in Python which says that if this results in four fields, okay, first field would go to this variable, second would go to this variable, third will go to this variable, and fourth will go to this variable. Okay, this is a very cool way in Python to assign together multiple variables. All right. So when the splitting happens, there will be four values. First will go here, second will go here, third will go here, and fourth will go here. Good. And all we have to do is now print, say, what do you say, movie ID plus tab plus, let me just for the heck of it put user ID. Okay. And let's test it if it is working or not. First of all, I need to chmod mlmap.py. Good, it is done. Now next thing I'm going to do is uh, Hadoop fs minus cat. Okay, what was that file name? Slash data slash ml 100. What was that? What was the file name? This is the file name ml-1m ml-1m and ml-1m and then ratings.dat slash ratings.dat. I'm testing it offline using the pipe. So I'm saying get the data from HDFS, print the data from HDFS, pipe the data to my recently created command, and put more, meaning show me page-wise the results. You can see that it has done the good job. Correct? You can see 1193, 661, and 941. 1193, 664, and 941. And these two, the key values are separated by tab. Okay? Everybody with me? So we have written a simple program which does this job. Okay? What was the name we were saying? mlmap.py. Okay? mlmap.py. Okay? I'm pasting it here, but you will have to format it by yourself. That's the only challenge you have to take. Because if I copy paste whatever I have just now pasted, it is garbled completely. Okay? So you'll have to make sure that you are also, if in the local file system, you should be able to see my file and it is pwd. If you type on your machine cat this slash mlmap.py, you should generally see this file. Okay, so I have opened my home directory for reading by everybody. Okay, if you are on e.cloudxlab. All right, so everybody with me? All right, is everybody with me? So our program did work offline, right? Now the next thing we want to do is we want to count number of occurrences. Or let me just do this. Let me modify this program, and because okay, let me just put tab slash one. I'm just putting one instead of user ID. Okay. Okay, so I'm just putting one instead of that. Now, what are we going to do is we are going to say Hadoop jar and our up to here, up to the jar file, the whole process remains same. Okay, and we are also not saying how many reduced tasks do we need. What happened to this? Okay, let there be two reduced tasks, or maybe we can make it three this time. Okay, and then we are saying in this, what is it that we want to do? We are saying ml 1 million slash ratings dot dat. Okay, is that the file name? Ratings dot dat ml dash 1 million. Good. And then I'm saying output is ratings count per movie. Okay, so I'm saying this is the mapper, and mapper is this time our mapper is going to be mlmap.py. Now everybody, the unique minus c would remain as such because we are just trying to count the occurrence of every movie. Okay, we are just trying to count occurrence of every movie, and therefore that will remain the same. Now we are going to pass, because our file does not exist on every node, so we're going to pass that as a file. Now let's see if it works or not. Okay, this is something I've not prepared so far. I've just done it during the class. Okay, so let me just open my. Also, a better way of seeing your job status is by going to job browser, and it shows you that it's running the file. It says the job could not be found, cannot assign the requested head and title. Okay, it has now succeeded. For some reason it doesn't show. Okay, now let me see if it has created a file or not. Okay, what was the name we had given? Let me sort it by date. Ratings count per movie. So as you can see that there are three parts, 0, 1 and 2 now, because we gave three reducers, right? And now let's see what's inside each one. So you can see that for every record our unique minus c was called, which means 104 is rated by 101 people, 1007 was rated by 232 people, and 101 was rated by 253. If we had not printed one here, one, then we would get only the movie ID. Okay, because unique minus C applies on the whole row. All right, everybody with me? Good. All right, I'm going to save the command here so that everybody can try it out. Okay, so let me just copy paste it. Okay, so this is the file. All right. Akash, Ajay, Akshata, Anil, Ankit, Anuj, Balvinder, Josephine, Kanan, Nandkumar, Pawan, Ravichandran, Ravindra, Robert, Samip, Tracy. Are we all on the same page? Great, great. All right. So basically, what was it? Yeah. Good. So basically, we did a quick MapReduce, this time using Python. Earlier, it was purely using Shell. This time, it was hybrid. Mapper was in Python, while the reducer was in Shell. Okay, so you can see clearly the input that reducer get is key and the value produced by the mapper, and this is sorted alphabetically, this is sorted lexically. Okay, if you want it to be sorted in a numeric fashion, you can specify that as part of the command line argument in streaming. You could say that do the numeric sorting instead of this. Okay, and it'll do the numeric sorting for you. Here you can see that 1004 is lesser than 1007 and 101 lexically is bigger than 1007, right? Similarly, 10010 is lexically bigger. Lexically means the way things are ordered in a dictionary. In a dictionary, A is A comes before AB, right? Similarly, the length, in case of lexical, length matters instead of the position only. All right. So you can see that we were able to compute the ratings per movie. It was very simple. We simply spit it out every movie and did a unique minus C on the number of movies. That's all. Okay. So we could extend the same example to a couple of more, and we can do many things using the same mechanism. All right. Now here we go. All right. Now let's take these four cases and try to understand how to solve complex problems using MapReduce. Is everybody ready with me? Okay. So the first question is, let us say you want to count the frequencies. Do you need MapReduce? Do you really need MapReduce to count frequencies of letters? The result will be essentially 26 numbers. How many times A has occurred and B has occurred and up to Z. There will be 26 numbers in the result. Do you really need MapReduce? If yes, yes, that's a good answer, Pavan. Depending on the input size. If the input is really, really big, then you need the MapReduce. Otherwise, you don't need MapReduce. Good, good. And a typical input size that people have tested out is that in this kind of cases when there's not too much of processing, it's only data reading. In those cases, 15 gigabyte is good. When RAM is not an issue, it's only the disk read is an issue. In those all cases, keeping the network bandwidth and everything, people have figured out around 15 gigabyte as the point at which you should prefer MapReduce over the single machine. Okay, 15 gigabyte is for the cases where the data does not get loaded into memory. Okay, while in case data gets loaded into the memory, the data size could be quite low, as in even if the data, let's say you have a 1 GB RAM or 2 GB RAM or 4 GB RAM. Let's take a case of practical case that your computer has say 4 GB RAM and you want to compute something really big. Okay, something say bigger than 5 GB RAM. Okay, in those cases, even for 5 GB data, you might need multiple computers or MapReduce. Sometimes your problem is fairly complex, such as finding recommendations or such as organizing things into categories. So if the problem is fairly complex, in those cases as well, for very small data, you might have to use either the supercomputer kind of things or a MapReduce kind of environment. All right. Now, question is, how do you do the MapReduce for the computation of frequencies of letter? Some of you have come up with the answer. I saw some MapReduce submissions. Okay, quickly. What will be the key and what will be the value? Yes, correct. That is the answer is correct. So yes, that will be the simplest way. Without MapReduce, this is what I will do. I'll create an array A of 26 size, scan the correct text character by character, scan the text character by character and increase A0 for if increase the zeroth value in this array if the character is A or capital A, increase 25 A25 for Z or capital Z or Z and others in between. All right. So essentially, I'm going to scan the text from left to right and update this array. This is without MapReduce. Okay. The next is with MapReduce. Okay. Without MapReduce, we know that RAM is not an issue, but network or disk I/O will be the bottleneck, right? Now, as you have said, I would actually, instead of just spitting out character and one, I will actually do the counting of letters in every line. Okay? I'll do the counting in every lines. I'll use the previously explained program where I'm maintaining array of 26 numbers and then every line will spit out the counted frequencies of the letters. Why am I doing this? Because I don't want to increase number of keys too much. So per line, I'll compute the frequencies and print. And we will do the same thing across all the mappers, and all the mappers will send the output to the reducer. Okay? And we'll sum up the things at the same time. All right, that's not a big deal. So I think everybody can achieve the results. We will optimize the character counting problem when we talk about combiner. We will see the drastic difference of using a combiner as opposed to using this. We will talk about combiner a little while later because in the previous case, a lot of transfer is happening between mapper and reducer because there are too many characters, right? Every key is so total number of keys will be total number of characters in the output, and therefore, it's going to be a big data transfer cost. Instead, if we could summarize the data on mapper node, it could have been faster. All right. Next is next way of solving. There could be many ways of solving each of these problems, and you must try couple of ways and observe this data. Observe this data, how much time it took overall. Okay, how much time it took for these operations. So you must try a couple of techniques for solving a single problem and observe the difference between various numbers. All right. Next is finding anagrams in a huge text. An anagram is basically a different arrangement of letters. So what will be the key and the value as mapper? What do we want to do is we want to bring together the words which are anagrams of each other. How do we do that? Yes, we want to choose a key such that that key should be same for all the anagrams of a word. What is an anagram? Anagram is a rearrangement of letters. So it is guaranteed that all the words which are anagrams of each other have the same characters, just that they are arranged in some way. If we dearrange them or make their arrangement same, then all those words will result in the same set of same word, right? So we choose a key such that the arrangement of the letters in each word is destroyed so that all the anagrams of a word would have the same key, right? That's right. Yes, by sorting letters of the word, because if we sort, we are basically dearranging the letter, and all the anagrams, whether cat, tack, or act, they will all result in same word, right? If you arrange the letters of cat, it will be A, C, and T, because A is lesser than C is lesser than T. Therefore, ACT. If we rearrange the letters in a word, you'll get that. And TAC, again, it's basically if you arrange the letters, it'll be ACT again. All right. So for all the anagrams of a word, we are going to get the same result. Okay. Any other suggestions? Balvinder says, would you group them by the length first and then sort? But that would not resolve our problem. Even if we have same length words together and then we are sorting them, then also the chances are cat and catty we are going to get together, right? Nearby. Sorry. Uh, okay. So any other suggestions other than this? The one which we are discussing now is this. Okay. So mapper will convert the input line into one word per line, and every word contains the key which is formed by sorting the characters of every word. The value is the word itself. Value is the word itself. So the is a value, and the key is formed by ordering the characters. Why are we ordering? So that our data is grouped together such that in the group all the words are anagram of each other, right? Because all the anagram will result in the same word if you rearrange their characters alphabetically, increasing or decreasing. Okay. And so what we are trying to do here, we are trying to play really clever. We are trying to exploit MapReduce, or we are trying to exploit group by the key, right? We're trying to exploit that property of MapReduce in order to solve our anagram problem. Okay, so we cleverly framed this key such that all the anagrams, when MapReduce comes and looks at our data and groups it based on the key, all our anagrams will automatically be together. Okay. Everybody with me? So mapper spits out eht, the act, cat, right? It rearranges the letter of the word and form the key, and the value is the word itself. And once it is arranged by mapper, they will look like this. Okay, so cat, the values will be these. Sit, the values will be this, and so on. And the reducer does nothing essentially. It just ignores the key, prints the values alone. That's the job of the reducer. Yes, everybody with me? Awesome. So let's move ahead. Any other questions at this point? Tracy, Robert, Samip, Ravindra, Ravi, Kanan, Nandkumar, Josephine, Balvinder, Anuj, Ankit, Anil, Akshata, Ajay, Akash. Good, good. All right, all right. Now the next question. I'm going to let you try this one. All right. So the problem 3A, which is there is this nice file that contains the username, space, the DNA, and we have to find people who have same DNA. We need to bring together the family which has the same DNA. Yes. So what is it that we are going to do here? All right. Okay. So Pawan says mapper is a key, sequence is the mapper, key is the sequence as in DNA sequence, and value is user ID. All right. So this is pretty simple. And thank you, Pawan. And anybody else? So this is our file where each line is user ID space the DNA and user. Then again, the second line is user ID and then TGCA. This is another DNA. Now what we want to do is we want to bring the users whose DNA is identical like this. User 1 and user 4 have identical DNA. User 3 and user 5 have identical DNA. Okay, so Pawan says that make the sequence as the key and the value as the user. Anybody suggest anything else? Yes? Any suggestions at this point? All right. All right. Great. Great. So this is fairly straightforward. Correct? So all we do is mapper key is DNA, value is the user, and in the reducer we just print the distinct users. Okay, that's all. All right. Before we move forward, let me answer Josephine's question. Question is, what if each word has um, many anagrams? So here we are not finding the anagrams as such. We are basically locating the anagram in the same file. Okay, let's say, so Because if you see here, there is this one toe. Toe does not have another anagram located in the same file. That's why. So, okay. And let me try to understand your question again. What if there are many anagrams? Meaning, there is a big word and this list goes really big. Is that your question? This list goes really big. But that would not be a problem. If that would not be too much of a problem. Say this list goes for say 10,000 record. The reducer doesn't have to load the whole thing into memory. It'll be read from the disk and we can save it further. All right. A question from Anil: how to eliminate duplicates? Simply print distinct values in reducer. Kind of yes, but the question is tough. Okay, so Anil's question is, how do you generally print distinct users? Although I can at this point say that okay, you use your standard data structures, standard sorting techniques, or standard unique functions, the way we did in word count. But imagine if there are users per DNA, a million users per DNA, then what happens? How do you do the reducer in those cases? We'll go into this case a while later. We will talk about this after a while. Okay? All right. Now, this is an interesting problem. Okay? And I'm going to give you a little bit more time to think about it. There is this file, again, the same file, and a researcher says that let's bring all the people who have identical DNAs as well as whose DNAs are mirror image of each other. He suspects that there's something called isomerism or something. I forgot. Isotopes, like which are optically they have the same one. Okay, I'll talk about it some other time. So here, what are we trying to do is we want to bring the users together who either have exactly same DNA or mirror image of the DNA. So all the users who belong to a group should have, who need to be grouped together, should have either same DNA or mirror image of the DNA. Meaning, what does it mean by mirror image? The reverse of the DNA. For example, user 1 and user 2 are mirror image of each other, ACGT and TGCA. If you read ACGT from the right to left, you will get TGCA, right? So the reverse of ACGT and TGCA. The problem statement is you have to bring such users together along with the users whose DNA is identical. Like user 1, user 2, and user 4 belong together. Okay? So what should be your strategy? And imagine that this file is say 20 gigabytes file. It has got billions of entries. That's correct. That's correct. We need to establish the logic for the key formation in such a way that original sequence and the mirror sequence have the same key. And how do you do that? That's the best way to put it, Pavan. So we have to establish a logic for the key formation in such a way that that ACGT, TGCA, and ACGT, they all form the same key. Akash says that key should be DNA and reverse of DNA sequence. Do you mean the concatenate the two, Akash? Then Both of the values. Okay. Okay. Do you want to order them in some way? If you are keeping the two values as, let's say, comma separated or something like that. So Ravichandran says, sort the letter of DNA, but then if you sort it, then user number 6, AGCT, will also come in the same group, right? Sameep's point is, order the mirror image in reverse order and make it look like original order and use that a key. But how do you know which one is the mirror image and which one is the original? We know that they are mirror image of each other. So which one do you uh, uh, convert, ACGT or TGCA? Because your logic is going to be executed against every record irrespective of what you code in. You will not have clarity whether you are on line number 1, 2, 3, or whatever. We'll go into what else you get as part of MapReduce. Okay. All right. I want to understand Akash's approach. And Josephine says, give common key for both. Okay, that's the catch. And what is it that we should give? That's exactly what we are trying to do. So what should be that common key for both? And all right. Yes. Okay. Okay. I think Pawan's approach is something I like so far. And I think Akash's approach is also good. Okay. Who else? So, yeah. There are many approaches to this. All right. All right. So, okay. Anybody else? All right. I'm going to move ahead. Here we go. Okay. So, let's take a look. What are we going to do is we are going with Pawan's approach and Akash's approach, where we generate for every DNA, we generate it reverse and we pick up the smaller of the two. We could do anything. Either we can order the two and pick up the max, or we could pick the min as in lexically min, or we could just concatenate them after ordering in certain manner. Now you can see clearly that when you order ACGT reverse, when you reverse ACGT, you get TGCA, and the minimum of the two is ACGT. Similarly, for user 2, if you reverse TGCA, you will get ACGT, and the minimum of the two is going to be ACGT, because minimum of two words, if you do lexically, is the way it is done in the dictionary. The one that starts with A is smaller than the one that starts with T. Therefore, for user number 2 as well, you get ACGT, right? Similarly, for user number 4, you will get the same key. Effectively, you will be able to solve the problem using this way. All right, everybody with me in this? So what is it that we are trying to do? We are trying to exploit the property of MapReduce that You give me the list of key and I'll group it together. That's the ability Hadoop gives us, and we are trying to exploit that property here, right? Good. Samir's question is, at the end, how do you realize which user have ACGT and this? That's why, although we don't need to find out whether user has the original one or not, but we could put that in a value. We could basically put in the value if we want to track it in the output. Okay. Right now, all we need in the output is the user ID. We want to bring the user ID together. We don't care. We don't need at the end of it what was the DNA of the person. If we needed, what we could have done is we could have just concatenated DNA in the value. Okay, good point, Samip. Now, now Ajay says that as an alternative approach, can we push the logic to the reducer side as well with proper partitioning? Okay. Can we push the logic to the reducer side? Let me think about it a little. But then, if we have to exploit the partitioner, right, then you'll need to have many reducers, correct? Because DNAs could be millions in nature. And if we plan that, okay, let this go to one and second, that is going to be tough. That is going to be tough because you'll have to have that many partitions. Or maybe I'm not understanding correctly. Yeah. So if you push ACGT and TGCA to the same reducer, you're going to have a partitioner which partitions the data into one record per partition, right? One record per reducer. That's going to be many reducers. It's going to be tough to ensure that it is going to be quite tough to convert ACGT into a numeric value such that it's the other values don't come to this one. Okay, because the chance is whenever we convert something into hash code, it's many to one relationship. Many strings result in the same hash code. Okay, yeah, good. But I like that you were thinking a little bit in a different side. So yeah, but yeah, okay. Nandkumar's question is, I'm not clear on your min approach. Do you use min to find the common key? I'm saying that pick the smaller one of the two. And when they say smaller, as in pick the one which is comes in the dictionary before the other one. So ACGT, if you have to put it in the dictionary, ACGT will be before TGCA. Either you pick max, pick min, or concatenate them together after ordering. The idea is you should get the single key, which is which is the idea is to mm, get the key which is same for all the mirror image and the same DNA. No, we don't give the min as the key. Here I've written that this is going to be our mapper's logic, which will basically pick the DNA, reverse it, and then find the min of the two. This is my key. This is my key. This is the output generated by mapper ACGT user 1, ACGT user 2, ACG user 3, ACGT user 4, ACG user 5, and AGCT user 6 and AGCT user 7. Okay, do I make sense, Nand Kumar? So this way, I'm generating the key values. Should I repeat? So yes, so we can only give a single value as the key. We'll go into more details on how you can customize your sorting algorithm, and in case you want to sort numerically, not lexically, that's another case. Yes, that's also correct, Akash. So Akash's point is, can we also do this by concatenating DNA and its reverse value and sort that word? But that will not solve the problem. Let me see what happens. So let me see. This concatenate verb with the reverse, okay, and this concatenate with reverse, okay. Now if we try to reverse it, it's going to be weird, right? What will be the reverse of this one? Let me open here. How do you reverse it? There is no reverse function. All right, I'm just trying to see. Okay, so the reverse of it is going to look like ACG da da da, and here the reverse of it is going to look like TGCA, right? So it's the same DNA, it's just that I'm concatenating this. But if you sort it first, all right, I think I got what you meant. You meant that sort these letters, right? Sort these letters. Mhm. If you sort this letter, what would happen is, as I said earlier, this also will be having the same results, right? T, C, G, A. If you sort it both, if you sort, then, right? So it's going to have the same result. They will all be resulting in same, correct? Therefore, the logic might not be the same. Okay, so how do you say sorted? All right, you can see that sorted of is same, correct? All right. Okay, so is my approach clear? How is the user 3 got ACG? Let me take a step back. Okay, so for ACG, what would happen is, let me copy the question as well, because at the later point of time, when you are reviewing these class notes, you are going to see this. Okay, so yeah, so you have user 3 got ACG, right? So what is the reverse of ACG? Reverse of ACG is GCA, correct? And the min of ACG and GCA is ACG. Make sense to you now? The overall idea is to bring together the users who either have identical DNA or they are exactly reverse of each other. Okay, I think we call them isomers if we have optical isomers or something like that. I've forgotten the names. Okay, so the way we are doing right now is twist our, I mean, reverse our word and pick the smaller one. Okay, if you're picking the bigger one, pick the bigger one for all so that you always get the same DNA. Okay, all right, all right. So good, good. Is everybody with me, or have I? Yeah. Okay. Okay. Should I move ahead? All right. So we will talk about the problem number 4 after the break. Okay. So we are going to take a break for 10 minutes and back by 10:46 p.m. IST. Sorry, it is at 9:46 p.m. IST. All right, so I'm back. All right, so I'm back. And regarding the assignment date, it would be better, the sooner the better, actually. Okay. But all the assignments need to be submitted before the submission of the project. Okay. All right. So I would prefer that you submit your assignments as soon as possible so that we can evaluate it as soon as possible and try to give you the feedback, and so that we can answer your questions and you can move ahead to the next session. Okay. I mean, although you will move ahead, but you won't be too confident. Okay. All right. All right. Okay. So everybody back. Should we start now? So we are about to start the problem number 4. Okay. So there is this strange democracy. Okay. In this democracy, not everyone is equal. The vote count is a function of the worth of the voter. Okay. Although everyone is voting for each other, but not everybody is equal. So, in this democracy, when people are voting for each other, and and you are also given their bank balances, or you can say that their credit rating from the bank, and based on that, you have to tell who got how many votes. Okay, for example, voter A has voted for C, B has voted for C, C has voted for F, and A has voted for B, and F has voted for C. Now, C was voted by A and B and F. So, C's overall vote count will be the worth of A, B, and F. Okay? Summation of the worth of A, the bank, I mean, as credit ratings of A, B, and F will be the worth of C. F's worth will be F's vote count will be equal to the worth of C, and B's vote count will be equal to the worth of A. Meaning, now let's take a look. Now the second list, you're given two lists. List 1 contains who voted for who. List 2 contains the worth of each person. Okay, the overall vote count would be, since C was voted by A, B, and F, the vote count will be 5 plus 1. And since F's worth is not known, we are assuming F's worth to be 0. Okay, so C's overall worth is going to be 6. All right, 5 plus 1, A plus B, because C was voted by A and B and F. And F is not given to us, so we are assuming the worth of F to be 0, and A and B is given here 5 plus 1. Therefore, 5 plus 1 plus 0 is the worth of C, a vote count of C. Okay. Similarly, for A was voted by nobody, therefore A's vote count is 0. B was voted by A, and A's worth is 5, so B's vote count is 5. Now uh, I mean C was voted by A, B, and F, so their vote count is 5 plus 1 plus 0 because F does not have a worth. And similarly, going ahead, A, B, C, D is voted by nobody, so D and E were voted by nobody. Therefore, their worth is 0. F was voted by C, and C's worth is 11, so F's vote count is 11. Alright, so you can see clearly, although in a good democracy, C could have won, but it's F that won because F was voted by C, who had the maximum bank balance, or you can say maximum worth. Okay, is everybody with me? Good, good. So now, question to all of you is, how do you write MapReduce? I'll give you a couple of hints before we start thinking about it. One, it's okay to concatenate two files. Okay, it's okay to concatenate two files by the use of MapReduce, in the sense that you could put these two files, list1 and list2, in a single folder. So when your mapper runs, you will get the records from both of them. Okay, so even in the word count problem, although we have data only in the big.txt file, if we had 20 such files, if we had 20 such file like big.txt, it could have been the same result, meaning our input can be a folder. And if it's a folder, all the files in that folder are concatenated together and fed to our mapper as if it's a single file. Okay? Now, the second thing that we are going to think here is these there can be many phases of MapReduce to solve a problem. And each of these phases, MapReduce 1, 2, 3, and 4, they can be individual separate processes which run one after another, second one reading from HDFS the output folder of the first one, and so on. So you can chain MapReduce jobs. Okay, the output of MapReduce phase 1 goes to the HDFS, and the second one reads from that folder where it has put the output. So there could be a problem could be comprised a problem could be made up of multiple MapReduce phases, okay, or you can say multiple MapReduce processes. All right, so any suggestions at this point? Balvinder says that the logic should be that key equals to replace voter with their worth using value equals to 40 reduce sum. Yes, that's exactly it is, right? But the problem is that for replacing the value from the second one, we cannot load the list 2 in the memory. The list 2 is really big and you cannot load it in memory for the list 1. Okay, so if we are iterating through list 1, we are let's say we're putting list 2 in the distributed cache. Okay, distributed cache is in we're putting it in a file and shipping it to the MapReduce. MapReduce can actually say cat second file and load it in the memory. Okay, in the if we are shipping it using minus file. Now we could do that. Okay, and on every node where we are executing map, we load the second file into the memory, replace the worth of the voter using in-memory hash map, and then print out their values. That could be one of the solution. That's called map side join, right? That is called map side join. We'll talk about map side joins when we talk about Java. And then, okay, so here the only problem is the list 2 is also very, very huge, so that you cannot load it in the memory. Okay, had these two files, list1 and list2, been in databases, what will you do? What will you do? You will join the two tables. You will join the two tables based on the voter, right? Voter equals to person, and we join the two, and then we group by the result, group by the voter, group by the voter later on, and sum up the worth. Correct? So we join list 1 and list 2, had it been the database. Now here is the teaser for all of you. Let us say, okay, have you used union in databases? Can we use union and group by to emulate join? So what is a union? Union is concatenating two files in a back to back and creating a single file, or joining two, I mean concatenating two tables. Okay, let's say you come to know about this database which does not have join but has union and group by. What does union do? Union basically puts one data set above the another such that they become the single data set. All right, all right. So here what we are trying to do right now is, as part of this exercise, we're trying to understand how is join implemented using MapReduce. Okay? Okay. So question is, can we use union and group by to emulate joins here? What is a join? Join basically brings together two records from two data sets based on a certain criteria. Here, the criteria is equality. So now, if you see the phrase, if you see the sentence, the join brings the record from the two sides together, right? Based on the equality of two columns, right? Similarly, here we are trying to bring the worth of the voter and the votee together. And how can we do that? If we concatenate list 1 and list 2, and then we group by the values by the person, then we will get the result. That's right. So the problem with this mechanism is that we don't have a join in MapReduce, and we are trying to figure that out using that. So that's right, Akshata. So actually, it could have been really, really simple. Okay, let me also understand and try to see from your point of view. Okay, so in a classic database, this is what you do. Select b.person from, select distinct voter from the list 1 and union all. Okay, select this b good, good, list 2 good, and then left join. Okay, so again, here the question was that we have to not use the join in order to compute the union. We want to do the join using union and group by. All right, we could actually do this. So if we form list 1 and list 2, we union them such that this column and this column sit on top of each other, and then we have this. Okay, and then we group by this person so that these records come together. And at that point of time, we'll know that and then we go ahead and form another system. I'll go into a little bit details now. All right. Okay. So somebody has implemented in Pig and Hive the same problem, and I'm pretty happy that lots of people are using my problems outside. And then, yeah. Okay. For those who are wondering why this weird problem, this is essentially a simplified page rank. Okay, this problem is a simplified version of PageRank. And what exactly is PageRank? PageRank was the reason why MapReduce was coined in the first place. So PageRank was the reason why MapReduce was coined in the first place. And what exactly PageRank do? PageRank is an algorithm from Google based on which Google became Google, based on which you get the good results above the bad results in Google search. When you search for something or somebody in the Google, you get the results ordered by PageRank. And how does that algorithm work? The algorithm work by ranking the pages based on number of votes. When your website links to my website's worth goes up. If my website is linking to somebody else, my website is essentially giving the vote to that website, and the vote count of my website matters a lot. If a very high rank website or very high, so the page rank of my website, let's say we have 20 people linking my website, so my website's rank is somewhere around 20. So I go, so and now if I refer to somebody, I'll be giving them 20 votes. Therefore, this whole mechanism of kind of a social credibility system is built using the PageRank algorithm. All right. So this PageRank algorithm is quite powerful, whereby pages vote to other pages. I mean, the Google computes the page rank. So a page which is linked by everybody directly or indirectly across the globe has got highest page rank. Okay, it has got highest page rank, and that's the beauty of page rank algorithm. Now, page rank, since it has to do the computation over billions of pages across the globe, or hundreds of billions of pages across the globe, it was impossible to do that kind of computation either with supercomputer or supercomputer or whatever. And that's where they came up with HDFS, they came up with MapReduce. Okay? So this problem number 4 is based very simplified version of MapReduce. I have simplified version of PageRank. I'm inspired by the algorithm, but this is a far more simpler version of it, and it's essentially a join. Okay, there the worth and the vote count is the same thing, and it is recursively defined in the standard PageRank. All right, let me show you what I'm trying to show. Okay, so first, list 1 and list 2 are put into a single folder and given to my mapper, which means the two files got concatenated, list 1 and list 2. Okay, so you got this. It's equivalent of doing the union. A5, B1, C11, D12, AC, AB, BC, and everything is a string for now. We'll talk about, because this looks like a number, but we are treating it like a string. Okay, so we are here at this point. Now, So mapper formed the key like this. Hadoop ordered and grouped it like this. Okay, Hadoop ordered our output of mapper like this. Now what do you see? It shows A voted B and C, and A's worth is 5. You might question that why is 5 before others? It is not. Okay, it is not. We will talk about that how do you order values as well. Okay, there is a way of ordering values as well. So for now, okay, for now let's assume that the first value is the number and the rest of this. So what did we do? We basically put the two files on one top of each other such that voters worth as well as the people who got voted by one person come together. So here every record, let me read it out. What does it mean? After Hadoop has grouped it for us, okay, after the output of mapper has been grouped by Hadoop, what does it mean? It means A voted for B and C, okay, and A's worth is 5. Similarly, B, B, whose worth is 1, has voted C, has voted C. That's what this record means. Now, the reduce phase is doing very interesting thing here, or it could skip the work and give it to the next phase of map reduce. But so here reduce will get each record like this. This is key and the group of values together. And what is reduce doing? For every key values, it is printing only the values and how much they got, the vote count. Okay, so when A voted to B and C, how much vote do B get? B gets 5, C gets 5, and A got nothing. This we are doing in order to have zeros in the output. Okay, then as a result of the second voting, who got what? C got 1, B got nothing. As a result of third voting, as a result of third voting, F got 11 and C got 0. Similarly, as a result of D12, this one, D has voted for nobody and D's value is 12. We get D0, D got nothing because nobody gets anything out of voting to somebody. But somebody votes them, they get the value. So we are trying to prepare a list of all the values, all the votes each one has gotten. Okay, so that's what is being done by the reduce phase, and you can see that now if we group it and sum it, it'll be the vote count which everybody has accumulated. All right, and why did we print A0, B0, C0? Because we want in the output this A0. All right, if we did not want this in the output, we would rather be, you know, happy with the standard way. All right, if a problem statement was that we don't care about this and these two, then it could have been fairly simple, as in we don't have to print these these or this. Okay, all right, is everybody with me? I've removed the zeros to make it simplified. So A voted to B and C. Because of this voting, B got 5, C got 5. We are listing down all the values everybody has accumulated. So B voted to C and B's worth is 1. So C got 1, F got 11, D has not voted for anybody, and F who has voted for C but But f's value is unknown, therefore we are skipping this. And then once we get this list, grouping it by the first column and summing it up is fairly simple. Okay, everybody okay with me at this point? All right. So this is how join is done underneath using MapReduce. There could be multiple ways of joining. Some of you have already answered. We load the list 2 into the memory and we run only the map task here, replacing the votees value or voters value, and then do the group by later on. That could have been another way, right? Feel free to question at this point. I know that there will be few things which I have not answered. Yeah, so yeah, this will help. But yeah, but they don't have a mechanism of uh, worth system. Everybody gets one vote from the one voter. So there are two MapReduce phases. First MapReduce phase has given us this one, and from this line you see here, the second MapReduce has started. Okay, here the mapper is not doing much. It's basically printing the values as such, whatever it's getting, and reducer is basically grouping and summing up the values. Second MapReduce phase is quite straightforward. First MapReduce phase has given us this list of values of each one. We just need to group and sum it up. Okay. So this second MapReduce, the map is not essentially doing much. It's essentially printing the same values. Okay. So I have not mentioned that map. Okay. So everybody with me on this? Any questions? So here the main problem that we try to solve, okay, I'm hanging on. Main problem which we have tried to solve is what if we try to join two humongous data set, and the only thing we have is group by. Group by as in map reduce. Okay, so what we did was we concatenated the two lists, and on the we concatenated such that the key we form out of map reduce is the column on which we are trying to join the two data sets. Yes, practically the second MapReduce input folder is the output folder of the first MapReduce. That's correct. All right, great, great. I'm hoping that everybody is with me because I have a little question that if there are no questions, that either either means that everybody has understood it or nobody has understood it. Ajay's question is, what is the programmatic way of specifying the same pipelining? Don't worry, we will go into this. How do you pipeline your MapReduce task? There are around 4 methods. We'll discuss 4 of them. All right. Okay. All right, all right, good. Now let's move ahead. Now, although you will find most of the people saying that you can solve every problem with MapReduce, but there are many cases which should not be or which cannot be converted into MapReduce. Yesterday we talked about one. There are a few more limitations and why not to use MapReduce. One, if the job can be done by a single machine in a reasonable time, even in production and even in the large scale scheme of things, meaning after 5 years or after 2 years, if you think that a single machine will be able to handle the data happily, then not use MapReduce. MapReduce is not a design pattern. MapReduce is not best practice. MapReduce is used when the data is huge and we cannot use the local machine. It's an overhead. It is sloppy and slow for the small data sets. It's slower if you are trying to use the small data sets in MapReduce. Your database will do a better job. Your local program will do a better job than the MapReduce on small data. Second, you should not be using MapReduce if your computation depends on previously computed values. Okay, one of such cases is, let's say you are about to generate the Fibonacci series. There are many such cases where the computation depends upon previously computed values. Specifically, the problems involving dynamic programming, in which you need the previously computed values for the next computation. Okay, that's why lots of machine learning or deep learning is still happening on multi-cores, because on every data set, the whatever learning is there needs to be shared amongst another training part. So every records training requires previous records training. In those cases, you cannot use MapReduce. Okay, so whenever the inference of one data set is needed for the computation from the another data set or the next data set, and you need to do it quite often, it's very difficult to use MapReduce. You need to do a very careful planning in these cases. Third is when you need real-time response. Because MapReduce has been designed in a batch way, there is an overhead of preparing map jobs, reduce job, getting the sorting done, moving the data to HDFS. There is a considerable, not reasonable, considerable amount of overhead. The map task, even if you're churning 1 kilobyte of data, might take something like 5 to 10 seconds. Okay? Therefore, therefore, if you need real-time response, it's not advisable to use MapReduce. If your algorithm depends on shared global state, if your algorithm, for every record processing, you need to make a call to a database, which is centrally located, then it is not suitable for MapReduce, because the whole purpose of distributed computing is defeated when there is a central resource on which everybody depends. So that central resource is the bottleneck for the computation of everybody. Therefore, MapReduce is not generally advisable in these cases. But why I'm saying this? Because some of us treat everybody like a nail if they have hammer. Okay, so I mean, when I've seen in the computation, everybody uh, tries to convert every problem into MapReduce. That's generally not required. Okay, most of the problems can be done very well using a single computer. It's only in the cases where workload grows beyond few gigabytes. In those cases, you should consider using MapReduce. All right. All right. Next is when you want to test MapReduce the way we did just now, you should always be testing MapReduce first on a small data. And when you're picking up the small data, pick a random data set, random sample from a big data set. Don't use head or tail. The big.txt is one such example. If you pick the big.txt, the first 10 lines and last 10 lines are very strange. Okay, so you should generally pick the random data set while testing. Second, always test mapper and reducer separately. And in case of streaming job, we did execute using, we, the way I was just doing in the class, we tested our mapper locally by using Hadoop fs minus cat and then piped the data to my program and then tested fine that this is working fine. Now it's ready to be given to Hadoop, right? So you should always test the data, test mapper and test reducer independently first, and then test concatenating the two by sort command. So you can kind of emulate the map reduce using this. Whatever is the input file, you concat it, as in print it, and then give it to the mapper, sort the data, and then give it to the reducer. If you are using streaming, you can test it using these commands. Okay, and whatever is the result, you can save it in the output and test it, check it whether it's giving the correct results. So when you are solving these four problems using streaming, you can use this kind of pipeline. All right, so if you are using Java, you can use mrunit. I'll go into the details. And if you are testing predictions, this is very important. Split the two part chronologically or in some other manner, and then generate the predictions from the first set and then compare the predictions against second set. Meaning we broke down the ratings of the movies of which was given up to say 2010, right? So we broke down the full predictions into up to 2010 and up to from 2010 to 2016, right? Now, based on this data, we started predicting that these users may also like these movies. And then whatever these predictions are there, we compare with the records from 2014 till 2010 to 2016. Why do we do that? Okay, so that we know that our algorithm is functioning correctly, right? This is the way Netflix did the challenge. So what they did was they took their data set. There were 1 million ratings given by the people. Half of the ratings was cleared and half of the ratings was kept. Okay, so based on the first half, you have to guess the second half's ratings, and then internally they were comparing that with the actual. Okay, so whenever somebody comes to you and tells you that hey, I can predict the future, or I have few recommendations to make, to check whether he is telling a truth, you ask something which you know already and then compare. It's the same thing which is done in testing predictions. Okay, because MapReduce is done a lot for creating predictions. So that's why I'm talking about testing at this point. All right. Okay. So assignment to all of you: code MR MapReduce for all the problems which we have discussed just now in your favorite language. Create a project on GitHub with your code and mention nobigdata.com in readme.md. Okay, so that's the assignment, the fifth assignment. Okay, the next assignment to all of you is you are given a huge text. You're given a very huge text. Okay, now you want to formulate the next word recommendation. All right, what you want to do is you want to formulate next word recommendation. How would you do that? Okay, so all right, let me take a step back. When you type a message in your phone, based on the previous word typed, it starts giving you the recommendation of the next word, right? Your phone start giving that, and that is done based on a kind of dictionary that they have generated, word and following 5 words. Okay, so that kind of recommendation they have generated, and as you type it, it looks into that dictionary or into that kind of pre-prepared results and gives you the suggestions. Now your job is to prepare that dictionary, prepare that list of word and the next word suggestions. For example, if you go through a big text file, you might come up with the idea that whenever people type happy, most of the people type birthday, then new year, or marriage. Okay, either people say happy birthday, happy new year, happy marriage anniversary. Or when people type how, the next word is my next word is either are, do, or did. So let's say you downloaded the entire Wikipedia, or let's say you download the entire chat records, and you want to generate this. What is it that you will do? Okay, what is it that you will do? So that's something that you have to come up with. Okay, so any questions at this point? Are the two problem statement clear? One was you code all these 4 problems in your favorite language, create a project on GitHub with your code, mention nobigdata.com in the readme.txt, readme.md, and uh, then let us know about your source code repository. Why we have created this way? Because what we believe is in today's time, GitHub is a very great place, and it will teach you few things. One, how to how to use Git. Okay, this will help you how to use Git. Git is a good source code management system. Even at Amazon, we started moving from P4 to Git. Second, we also moved from, second, almost everybody from Google, Mozilla, and everybody has moved to Git. Git is by Linus Torvald, the same guy who created Linux. So using Git, we were able to do better work than P4. That's why we moved at Amazon as well. So I would strongly recommend learning Git because it is going to replace almost every source code management system. Okay, I'll cover it, Pavan. All right. So you can download, if you are a little impatient, you can download from the No Big Data. There is a project which you can import, and there is also a small video which shows how to configure that. All right, now let's move ahead. Okay, so these 2 problems are clear to you. All right, let's move ahead. This is also done. This is also done. Now We are moving to problem number, slide number 4. All right. So we will go into, okay, let me wake everybody up. A quick recap, everybody are you with me? First, the data generated by mapper is given to the reducer and then it is sorted or shuffled. Is that correct? Yes or no? The data generated by the mapper is given to reducer and then it is sorted. Mhm. That's right. That's right. So the output of the mapper is first sorted and then reducers are called. Okay. Then given to reducers. Correct? Because all the values need to come together in the group. Next is the mapper can only generate a single key value pair for an input line. Correct or wrong? In our word count, did each line generate multiple keys or only one keys? Great, great. All right. The answer is no. Mapper can generate as many key value pairs as it wants for an input. Okay? That's the difference between our mapper and the mapper in classical way defined. All right? Next question is, a mapper always have to generate. A mapper always have to generate at least a key value pair. Can there be a line? Can there be a line for which mapper decides not to spit out the key value? Let's say there is a blank line and you don't want to spit out the word and the frequency. Can you do that? You can skip printing key value, right? That's correct. So, yes, it does not have to generate at least one key value pair. So in simple words, mapper can generate zero or more key values. Alright? By default, there is only one reducer in case of streaming job. Yes or no? No, by default, if you don't provide any number of reducers, in case of streaming job, it'll be one or more. That's right, it'll be one and more. You can specify, okay, you can specify the number of reducers by using the option mapreduce.task. You can say minus d space mapred.reduceTask equals to, the way we had done in previous example. All right. In Hadoop 1.0, what was the role of job tracker? A or B? Quickly. Executing the MapReduce logic or delegating the MapReduce logic to task tracker. That's correct. All right, that's right. The map logic is executed preferably on the nodes that have required data. Is that true or false? Yes or no? That's correct. That's good. Yes. So map logic, the mapper's logic is generally executed preferably on the nodes that have required data. Now, question is little bit twisted like your GMAT exam. Okay. The map logic is always executed on the nodes that have required data. Always. Is it true? That's right. It's wrong. Good. Great. Because if the node all the nodes that contains data or its copies are busy, it will execute on the nearby nodes. Now, where does Hadoop store the result of reducer? HDFS or local file system? That's correct. That's correct. Now, where does Hadoop store the intermediate data such as output of map task? Before sending it, it has to collect, and so does it create a local file system? Does it create a file in the local file system on every node or keeps it in HDFS? Okay. In HDFS, if you put any data, it'll get cloned 3 times, right? And so you don't want to keep the data which is redundant, which need to be deleted quickly, temporary data in HDFS. Second, in memory, if you try to put a lot of data, memory might overflow. Okay, so you always put the temporary intermediate data in the small file system. The way it happens is you keep on pumping the data into the memory, and periodically the data keeps on getting purged into the local file system. And why do we why do we put it first in the memory? Because when you put something into memory first, it's quick to write. Okay, and therefore it doesn't stop the other processes. And since disk seek is costlier, it is better to purge the data when it becomes a considerable chunk, because the main time in case of a disk write goes into seeking the disk location. A question from Anil is, how does other nodes get the intermediate data? The communication happens between mappers and reducers over TCP/IP connection, or you can say SSH, and that's how the other nodes get the intermediate data. All right. Next question is, the whole of the HDFS block available on the node is fed to the mapper. Yes or no? Okay, so this was a question which was something uh, be the foundation of our further discussion about MapReduce. Okay, the answer is no. Input is split using input splits, and okay, so since the HDFS block is raw data, the raw data does not care whether the boundary is in middle of the word or is middle of the sentence or is in the middle of character. Therefore, there has to be boundary shifting has to be done for every HDFS block, before it becomes processable. We will go into more details about it after we finish Java part. Okay, so why we want to discuss in Java? One, it has got primary support. We will go into more details, Anand. Okay, I don't want to open that box because it's going to take a considerable amount of time. Okay. All right. So first, the very simple example is Java. The whole Hadoop is written in Java, so it's easier to customize a lot of things using Java. Okay, and therefore it's easier to write, easier to control a lot of MapReduce using Java, as you will see further. Okay, so but having said that, I have done 90% of my MapReduce coding in my career using Python. Okay, even though I'm good with Java, but still I was more comfortable. I even though I learned Python in order to do the MapReduce, okay, because the whole data science team was more comfortable with Python, so I learned Python for that, and then and found that it was I was quite comfortable with using Python for that. All right. Next is, so let's go straight. So one is, to get it done, it's easier to use Eclipse. So in Eclipse, you can create a Java project, add the libraries, okay, add the libraries, and then change the JDK to 7. Why? Because if you compile with JDK 8, the behavior is very different. The argument considerations are a little different and so on. Okay, that's why we'll change that. Second is, change the Java compiler settings to 1.6. Why? Because whenever you build something, whether it's an Android app, it's a website, or it's a Java compiler, you should be humble in your approach, such that your output can be catered to the lowest common denominator. Meaning, if you're building a website, build it for people who have even IE7. Second, if you're building the Android app, build it for the people who have old phone as well. Because if you build for them, it'll work for the newer one. Because almost every new version of the browser can read the older websites. Okay. So similarly, when you compile a Java code, you compile it for the target audience which had the older Java version. Because if you're compiling for say 1.6, it'll not run for 1.5, but it'll run for 1.6 and above. Therefore, taking this reasonable amount of you know consideration is very important. So 1.6 is good, and also in case of say your program, in case of MapReduce, since your program is going to be shipped to the data center, and data center has inertia to upgrade Java or any other such platform, because if they upgrade, it might break so many things, right? That's why there is a huge inertia to upgrade versions of various components. Ajay's question is, do these Hadoop libs need to be part of the final jar file? No. Hadoop libs are only required for compilation, okay, so that Java does not throw an error saying the library is not found. But these need not be shipped together with your jar program, because these are anyway part of Hadoop core library. Okay, while running, the same class will be found by Hadoop in its own library function. All right. So now let me first finish this part. Okay. So first thing you will do is the easier way would be to download the project from No Big Data and import it into your Eclipse. Easier thing would be to, okay, to download the project It takes a little bit while, not because of CloudX Lab, but because there are so many videos in this one, so they fetch the preview file. Okay, so here you have, yeah. So MapReduce framework assignment, fine. Yeah, here is the sample project. You can download the sample project, Java MapReduce example. Okay, it's getting downloaded. Now, what we want to do is we want to launch Eclipse. Where is our Eclipse? In case of Mac, it is here. Otherwise, you can download. All right, do we have Eclipse here? All right, I have downloaded it from Eclipse download. I've downloaded it from here. You can download for Java, that's good, or this one, any of this. Okay, so you can download from here, whatever version suits you. If your Windows is 32-bit, 64-bit, Mac, Linux, or anything, you can download from there. And once you've downloaded and you open, you can, all right, I'm launching the installer. Ouch. Okay, so looks like there is a mess up. To open Eclipse installer, you need to install legacy this here, and okay, all right. I hope this works. All right. If you have any questions before this thing gets downloaded, I'll love to answer that. Okay. So yeah. So I'm downloading the Java for my Mac. Okay. For you, it won't be too much of a problem because Java installer for Windows works pretty good. Okay. For on your desktop, you install Eclipse. Although if you're comfortable with IntelliJ, you are also fine there. Okay. The idea is very simple. You create a project, whether in Eclipse or IntelliJ. All you need to do is add the libraries provided in this folder. Okay, I'll show you which folder I'm talking about. Version 1.6 or 7 is required. Wow. Okay. Alright, version this JVM is not suitable. Alright, install Java 1.7 Mac. Okay. So on the installation page, how do you download? Generally, I assume that it was supposed to be downloaded on Mac. It's a fresh machine. Okay. Which demo file? The demo file, basically the project is here. You can go to session 5 and here, sample project. And there, if you go down, you can see that how to configure the project in Eclipse. Here I have put, and there is one more note, how to debug. Okay. All right. I'll look into this. I'll try to install it later, but yeah, we can try to answer other questions at this point if you have some. Okay. Looks like these people have created a big mess. Okay, JDK download. And I say here I want this one. Alright. It says you have to accept the agreement. Alright. Looks like it'll work. Alright, I am hoping that will work now. All right, no worries. So if you have any questions at this point, I would love to answer them. So the general flow is going to be once we install Java and then install Eclipse, we will import this project. This project contains our code of MapReduce. And of course, we are going with the word count again. All right. So, okay, when you log in into No Big Data, you don't have access to those links. So when you go to My Courses, are you not able to see this particular course? So that's somebody's question that they are not able to see those links. You don't see this particular one? Please send an email and then we will enable you the access of this one. Okay? You just send us an email at reaches@nobigdata and then you can. All right. Any other questions at this point? So you can download any of the simple IDE. Before that, if you need to download JDK, but download JDK later only when Eclipse complains. Okay, because for Windows, the Eclipse ships with JDK, as per my understanding earlier. I'm not sure what they have done now. Okay, and then we'll import the pre-created project, and that's nothing but it's a simple project, a new Java project in which you will essentially add those libraries. Okay, the project which we are talking here, this one, it's very simple project. I could walk you through this one actually. Open with, let me drag it to my editor. You can see that this is the project. It contains two main folders. One contains all the libraries that are required by Hadoop. Second contains the libraries that are second contains the actual code. This src my contains the actual code. It has got four files. One is mapper, other is reducer, and next is the driver. Yes, that's right. So, Akshata, if you have finished the previous assignments, okay, or even if you have not finished, so one of the important things to do would be set up a Git project. Yes. Second is Eclipse download, and then all the assignments. Yes. Okay. Try to basically set it up. And so I'm trying to set up on the this thing on the Mac, which seems to be a little crazy. Is it done? I'm just hoping that everything will work now. Now let me just start the, where is my download folder? Alright, now this will install my Eclipse. Alright, so no worries. So we will go into more details next week. In the meantime, if you want to configure, just follow these instructions and configure the projects. And we will discuss how to do MapReduce in Java. And then we will talk about advanced topics in Java. Okay, so next week's work is going to be quite related to Java. I mean, specifically the Saturday one. And then we will go into Pig, Hive, and other topics. No worries, Nandkumar. I'll try to make it fairly simple. All right. And if you have not worked much in Java, in your courses, you will have some time to review the Java class. There is one Java class I had put here. It should be somewhere here. Okay. Are you able to see the Java class? No, Pawan. Actually, these slides are not equivalent of the sessions because what has happened is that uh, the course has been increased. Okay, course has been increased. We have added more and more topics, and that's the reason it is 6 classes. So nothing to worry. Don't go by that session 4, session 3. Just go with what we are, the way we are doing, because it's difficult to keep the sessions as well as the course curriculum in sync. We cannot never finish one chapter in one class, right? Because we cannot compress the curriculum to just fit 3 hours. Okay, that's the reason you will see this overflow. But don't worry, we will. Everything is going in the perfectly fine manner. All right, just focus on the assignments and the content. All right, great. See you tomorrow. See you next week. And if you have any questions, feel free to. Is there any way I can do a quick review kind of class on the topic that I'm confused on? Yes, you can schedule a one-on-one, and I'll try my best if I can help you with. Okay, all right, all right. Or one of my team members would also can also assist you. Okay, so if you could put down the general agenda, then I can plan. All right, just generally drop me 3 time slots. Okay, because there are other candidates also who want one-on-one. So Just drop me 3 time slots. I'll pick one and then confirm. All right. Okay, then. See you next week. Bye bye. Have a good day.